Hello everyone, this is Professor Songye from the Hong Kong Polytechnic University. The topic I'm going to present today is power performance of wind turbines in wake regions. The second author is one research assistant under my supervision, Mr. Songye. The wake phenomenon in wind farms is actually well known. These two photos show the visualized wake phenomenon in some very special weather conditions. We can clearly see some wind turbines will be located inside the wake regions of others. In fact, it's already known the wake effect in a wind farm will lead to reduced power production due to the wind speed deficit and increased fatigue damage due to the intensified wind speed fluctuations. The wake effects are a complex phenomenon. They involve multiple effects. So what are the contributions of multiple effects on these two aspects? It's still unclear. It's partially due to the modeling technique. For example, the CFD model. It's very time-consuming. The computational cost is very high. So it's very difficult to simulate the whole wind farm region using the CFD models. If we look at some analytical models, they are very simple, but sometimes they are oversimplified. They overlook some very important phenomena inside the wake regions. This table summarizes some commonly used wake simulation methods. We have some low fidelity methods. Most of them are based on some analytical models. They are very simple and efficient, but they cannot capture the details of flow. On the other hand, we have some high fidelity methods, for example, LES and DES. They are very accurate, but their computational efficiency is also very low. It's very difficult to simulate a large wind farm region. So a more realistic solution will be middle fidelity methods. We have multiple types in this category. In this study, we used this DWM model, which is available in the recently released Fast Farm software. This is also one of the middle fidelity methods I just mentioned. This slide shows the simulation framework of the Fast Farm software. It has multiple modules to simulate the wake effect. For example, this AWAE module simulates the ambient wind and array effects. This WD module will simulate the dynamics of wake. And this WAT module will simulate the increased turbulence inside the wake. These modules communicate with each other. Then finally, it interacts with this OpenFast software. Then the OpenFast software can simulate the dynamics and power performance of wind turbines inside the wake. The wake has at least three effects: the wind speed deficit, the wake meandering effect, and the turbulence intensity increase effect. The wake deficit evolution in the far wake region is calculated in the Fast Farm by the thin shear approximation of Rain's equation under quasi-static conditions. This wake deficit is determined in the AWAE and the WD modulus. In terms of the turbulence intensity, there are three components. The first one is ambient turbulence intensity in the inflow. The second one is apparent turbulence intensity in the wake. The third one is added turbulence intensity in the wake. They are considered using different methods in the Fast Farm. This slide shows the simulation model established in the Fast Farm software. We can clearly see two wind turbine models here. The front one is called WT1. The back one is called WT2. WT2 is located inside the wake regions of WT1. The Fast Farm software provides the possibility to simulate different types of wind field. For example, the first one is just a uniform wind field without any turbulence. The second one is to simulate the wind gradient due to the surface roughness, but still without any turbulence. The third one adds some turbulence inside the inflow, so we can see this turbulence. The fourth one, we can see this so-called wake meandering effect. We can see these ups and downs of the wake. In the last one, we further consider the wake added turbulence effect. So we introduce a more turbulence intensity inside the wake regions. This slide shows the simulated wind field in different cases. If we look at the first one, no turbulence, so we can see the wake region has a diameter very close to the rotor diameter. But in the second one, we considered turbulence. We considered the wake meandering effect. If we zoom into this area, we can clearly see the distortion of this wake region. This is so-called wake meandering effect. Then in the last one, we further considered wake added turbulence effect. So the turbulence intensity in this wake region is further increased. With this simulated wind field, we can quantitatively study the wind flow characteristics. For example, the average wind speed profile, the turbulence intensity, and the wake center variations. This slide shows the mean wind speed profile. The dashed line is seen by WT1. The red line is the mean wind speed seen by WT2. We can clearly see the gap. This is the wind speed deficit induced by the wake effect. Furthermore, with the increasing separation distance from 2D to 8D, we can see this gap becomes smaller. So we can see this wind speed recovery with the increasing separation distance. In the first case, we consider the steady wind field. In the second case, we added the turbulence effect. We added the wake meandering effect. We can see the gap. The gap becomes smaller compared with the first case. So this means the turbulence effect and the wake meandering effect can promote the wind speed recovery with the increasing separation distance. Let's look at the wind fluctuation in terms of wind speed standard deviation. In general, if we introduce the turbulence effect, wake meandering effect, and the wake added turbulence effect, these effects will increase the wind speed fluctuation, particularly at low and medium wind speed. This 12 meters per second is very close to the rated wind speed, but this increasing effect is not obvious at this high wind speed. We can further quantify the wind speed fluctuation using this turbulence intensity index. We can compare turbulence intensity for different separation distance 4D and 8D for different wind speed 6 meters per second and 12 meters per second. Let's look at this. The black bar shows the turbulence intensity in the inflow, its ambient turbulence intensity. The red bar shows the turbulence intensity in the wake region. We can clearly see the turbulence intensity in the wake region is much higher than the ambient turbulence intensity, particularly when we consider the wake meandering effect, consider the wake added turbulence. This has the highest turbulence intensity among all the cases. This one shows the change of the wake center position. In the first three cases, we didn't consider the wake meandering effect. So we can see the wake center positions are quite stable in these three cases. But in the last two cases, we considered the wake meandering effect. As a result, we can see the wake center moves in a larger area due to this effect. Finally, we use this table to summarize the wake characteristics. We simulated different effects in the wake regions, including wind shear, ambient turbulence, wake meandering, wake-added turbulence. We look at their impact on several major parameters: mean wind speed standard deviation, turbulence intensity, wake center position. The positive side means increase, the negative side means decrease. The circle means no impact. We can clearly see they have different impacts on different parameters. Let's look at the real impact on the power performance. Here I show two wind speed, 6 meters per second and 12 meters per second. Let's focus on this second case, 12 meters per second. It's very close to the rated wind speed. As a result, the power of the first wind turbine here is very close to the rated power of this wind turbine, 5 megawatt. But if we look at the second wind turbine, the power production will be much less due to this wake effect. More important, if we just use traditional analytical models to consider wind speed deficit in the wake regions, we will get this green bar. It will predict the power deficit is around 48% at 4D distance, around 33% at this 8D distance. But if we consider all the effects, including wake meandering and added turbulence, we will get the last bar. It will get the power deficit only 33% at 4D distance, only 20% at 8D distance. The power deficit is much less. It means the traditional analytical models will overestimate the power loss here. So if we want to accurately predict the power loss of these wind turbines in the wake region, we have to consider this wake meandering effect and the wake added turbulence effect in the simulation. If we consider very high wind speed, 18 meters per second, much higher than the rated wind speed, then even we consider the wind speed deficit in the wake region, the reduced wind speed is still much higher than the rated wind speed. Consequently, the power is maintained almost constant in the wake region, still close to 5 megawatt, so no significant impact on the power performance at this high wind speed. Finally, some very brief conclusions. The effects of wind shear, ambient turbulence, wake meandering, and wake-added turbulence are investigated in this study. The wake effect leads to obvious mean wind speed deficit, but the ambient turbulence and the wake meandering effect actually mitigate the wake deficit and increase the wind speed recovery. The wake effect leads to the obviously increased turbulence intensity in the wake regions. Consequently, in the power analysis, we have to include these effects, including ambient turbulence, wake meandering, and wake-added turbulence in our simulation to accurately predict the power performance. Due to the wind speed variation, the power of the wind turbines in the wake regions suffer more obvious fluctuation. Particularly, it's due to the turbulence effect. Due to the time limitation, I couldn't include the wake effect on fatigue damage in today's presentation, but the general conclusion is ignoring the wake effect will underestimate the fatigue damage, leading to unsafe design of wind turbines. Finally, I want to acknowledge the financial support from different funding sources. That's all for my today's presentation. Any questions?